vertices. Make sense? Then what? Then there's ratios, right? Um, so how they got this idea, I don't know. But it's what we're about to do is reasonable. We thought about it once, and it's a reasonable thing to attempt. And when you're interested in these type of things, and sit down and play a little bit, it's not hard to understand that one might bump into this kind of discovery. But if I give you 10 minutes and discover this, that's unreasonable, right? So let's look at it that way, right? Someone will bump into this eventually. So here's the idea: is that what kind of, other than this one, what formula do we have that uses sine, other than law of sine? Before that, what were you learning? Function of all angle. That's not quite the formula. It's some formula, clear formula. We're use some formula that uses sine theta. Area of the triangle, right? When I was introducing this area of the triangle, I said if you look at this angle, there's one way to what. If I look at this angle, what are the adjacents? B and C, and that's the only thing that goes into the formula, right? If I look at that angle, then A and C goes into the formula. If I look at that angle, A and B goes into the what formula? The area of the triangle. So this was a trick question. I probably asked this question. If it is exactly like this, if this is not just some arbitrary picture, if it is actual triangle like this, if you calculate area here or there and there using those formula, which one is the greatest, you think, among those? Which one is the greatest area you're going to get? Using this angle A, using that angle C, or using that angle B? Which one? It's the same area, right? Wherever you look at, how much of the water go into that, or that quantity will never change. So you really have to think about, so what is this idea of the area and all that. But if you believe area is something that never changes wherever you look at, right, then they all have to be the same. And it seems like an interesting idea because it involves all different pairs of this thing. All right? So let's write that down. Area of this triangle. There are three different ways to do this, right? So what were those three different ways? 1/2 times. How about AB? If I use A and B, let me unmute my phone. Sorry about this. All right. What should I multiply? Sine theta, right? But not theta here. There's no theta. What vortex are we using here? Vortex C. Thank you. All right? Does that make sense? So if you look at vortex B and vortex A, we have a similar statement, correct? So I'd like to leave it as an exercise. I want you to go ahead and write down, using this equal symbol is equal. It's not process. We're recognizing this is I realize some of the students look at this equal symbol as if it's some sort of process. It's not. We're recognizing this quantity and next two quantity are exactly equal. They're same area, right? So why don't you go ahead and write them down? Right? I'd like to make that was a little exercise today. All right, by looking at the other two vertices, I hope you got something like this. A goes first, B goes later. It doesn't matter, right? So it's already interesting, right? There's no easy reason to see by looking at it here that why these two things are equal to each other. Further, I'm going to just get rid of some of the things that are common and make this equality simpler, right? What are those factors? 1/2 are all common. If you get rid of it, they remain same, right? So here's AB sine C. It's like all letter appear in every part, right? A, B, C in this order. So AC is a missing letter. B appears in that sign. BC and missing letter A appears in that sign part. That's the formula, right? All right. If you want to change this one to the law of sines, what operation should we do? That was a tricky part, but that's a clever part. To turn this little bulky expressions to a lot simpler one is the next clever part. So they decided to make it this prettier by dividing everything by same quantity. Then it's going to remain same, correct? So that quantity was A times B times C. A times B times C, A times B times C. So if you divide everything by the same quantity, then they remain the same. Then it clears out lots of repetitive part and make a very nice symmetry that reveals. Sine C divided by what now? Because AB cancel as a factor, and then little c down here, right? How about the second one? Sine B, you see AC appears in here, AC appears down there. If they cancel, only leaving the B in the denominator. And if you look at the third part, there's a BC appearing, down there BC appearing. If they cancel out, it leaves a sine A divided by little a. So through this very simple algebraic manipulation, we turn this equation into very symmetric, and it's very easy to remember how they pair up in the triangles. All right? So if the guy in the street describes you all of a sudden and asks you why this law of sine is true, then your one-liner answer is that because the area of the triangles are all around the same, that gives you nice idea. The graph like this. That's my guy in the street joke. But that's why. Okay? Yeah, that's the